In section 3 of module 1, we're going to discuss electrophysiology. So this is lecture 1 of a 4-part lecture. So our objectives: describe the function of myocardial cells, define the function of pacemaker cells, list and describe the 4 primary properties of cardiac cells, list the 3 major electrolytes that affect cardiac action potential, identify potassium's role in cardiac depolarization and repolarization, identify sodium's role in cardiac depolarization and repolarization, and identify calcium's role in depolarization and myocardial contraction. So to begin with, let's talk about the cells. So we've learned in previous lectures that the heart is made of myocardial cells, which are your muscle cells. So it's the inner layer of cells that make up the walls of the ventricles and the walls of the atria. These are the contractile or the mechanical workers. So they're responsible for generating the physical contraction of the heart cells. They make up the thin muscular layer of the atrial walls and the thicker muscular layers of the ventricular walls. Their primary functions are both contraction and relaxation. Physical contraction of the myocardial tissue generates blood flow. With the pacemaker cells, which are your conductor cells, these are specialized cells. They're specialized to the electrical system of the heart. They make up the nodes in the conducting system of the heart, and they generate and conduct electrical impulses down the conduction pathway of the heart. So these are your conductors. These are strictly electrical conduction. The primary function is generation and conduction of electrical impulses. Now, in order for the heart to work properly, you've got to have your mechanical function, which is the myocardial tissue, and you've got to have your pacemaker function, which are your conducting cells. And the conducting cells are going to be the ones that cause the myocardial to be stimulated. So the myocardial cells actually respond to impulses from the pacemaker cells by contracting. So as we're thinking forward, when we're looking at cardiac issues, we know that in order for the heart to work right, the electrical cells and the mechanical cells, or the myocardial cells, have to work together. So cardiac cells are very unique. So they're different than any other cell in the body, and they've got 4 characteristics that are very important. The first one being contractility, which is a mechanical function. This is also referred to as rhythmicity, or the ability to contract and expand to form the actual physical rhythm. So the book definition: the ability to shorten and cause contraction in response to an electrical stimulus. Automaticity, which is an electrical function, is a really neat function, and it's the ability for the cardiac pacemaker cells to generate electrical impulses without external stimulation. Or another way to say it is the ability of the cell to self-propagate an action potential. Then you've got excitability. Excitability is an electrical function as well, and it's the ability to respond to an electrical stimulus. Sometimes this is actually referred to as irritability. So excitability can be good in the fact that it responds to an electrical stimulus, but excitability can also, or irritability can also be not so good when it responds to other stimulus, such as hypoxia or stimulants or something like that. And then conductivity, which again is an electrical function, and it's the ability of the cardiac cells to receive an electrical stimulus, then to transmit the stimulus to other cardiac cells. They function collectively as a unit. So in order for all of these to work together, they've got to essentially be a unit. So the electrical cells have to be able to respond to a stimulus and contract, and then they've got to be able to conduct the electrical stimulus through the heart cells to stimulate the mechanical function of the myocardial tissue. So again, these are going to be where you'll actually see these cell characteristics. So automaticity, or the ability to self-propagate an action potential, you'll see these in the pacemaker areas, such as the SA node, the AV node, or the AV junction rather, in the Purkinje network. For excitability, all cardiac cells, including myocardial cells, are going to respond to a electrical stimulus. Conductivity, all cardiac cells are going to receive the ability to conduct the electrical stimulus through the heart. And then contractility, this is myocardial muscle cells, and they are going to receive the stimulus from the conducting cells to contract. So a very important part of electrophysiology is the role that electrolytes play. So electrolytes, the definition, substances or compounds whose molecules dissociate into charged components or ions. If you've got a electrolyte that dissociates into a positively charged ion, this is called a cation, and a negatively charged ion is an anion. Myocardial tissue is actually bathed in electrolytes, and they play a huge function in the next part that we're going to talk about with depolarization. So potassium performs a major function in the cardiac depolarization and repolarization. Sodium performs a vital part in depolarization of myocardial tissue, and calcium performs an important function in the depolarization and myocardial or muscular contraction. Now, magnesium and chloride are also important cations, but sodium, potassium, and calcium are the ones that play a huge role in the action potential that we'll talk about. So the main positively charged ion in the body is sodium. The main negatively charged ion in the body is chloride. Other common ions which are positively charged are potassium and calcium. So the term bioelectricity. Bioelectricity is created by the movement of ions through a semi-permeable membrane. The main extracellular ion is sodium, so the main ion that's outside of the cell is sodium, and that's going to be important here in a few minutes. And the main intracellular ion is potassium, and in order for you to actually depolarize or create an electrical conduction, those ions actually have to move across the membrane. So with the movement of ions, the ionic difference on two sides of the cell, the potassium concentration is higher on the inside of the cardiac cell, and the sodium is greater on the outside of the cell. Now, the sodium-potassium exchange pump will come in towards the end of the action potential in order to get all the sodium out of the cell and the potassium back into the cell when the cell is ready to get into its resting state. During a polarized or resting state, the inside of the cell is electrically negative relative to the outside of the cell. So a visual here to see what we're talking about, if you can think of this area right here as the cardiac cell, it's more negatively charged than this area out here. So it's -70 and 0. So there's essentially no charge where the sodium is during the resting state, but there's a negative charge in the inside of the cell. I always think of it like this to help me put it in perspective. If I were to look at my bank account, I'd rather have $0 than for my bank account to show that I have -70. Because -70 is much more negative than a 0 is. So on the inside of the cell, you've got a high concentration of potassium. And on the outside of the cell, you've got a high concentration of sodium. So this is during what we call the resting potential. Resting. So in review, your three primary ions that we're going to discuss in the next lecture are sodium, potassium, and calcium. During the cell's resting potential, or the time that it is polarized or at rest, the sodium concentration is much higher on the outside of the cell, and the potassium concentration is much higher on the inside of the cell. Now, as we get into talking about depolarization, we're going to talk about the actual ionic movement of these electrolytes going from the inside and the outside of the cell. So this concludes Module 1-3, Lecture 1.